Hello and welcome back to Introductory Electromancy. Today we will be learning about diodes. Your friend the diode. Now, diodes are effectively one-way valves. They allow current to flow in one direction, but not in the other. There are a variety of different types of diodes. As with everything else in these introductory instructions, you could spend hours and hours or even entire careers studying individual parts and how they act. But since this is assumed to be an introductory experience for you, dear viewer, I am trying to keep everything summarized to the maximum extent possible while still conveying a useful amount of understanding. A typical diode is the 1N4004. This is a rectifier rated for 1 amp, 400 volts. It'll block 400 volts, allegedly. Really, you should only run everything at half its rated voltage. This is, as mentioned previously, called derating. So this diode functions as a one-way valve for current. It allows conventional current to flow this way, but prevents it from flowing the other way. It has a little silver band which marks the cathode, the minus terminal. Now, what makes a diode work? And what can you do with them? Well, there are light-emitting diodes. Those are the ones you're probably most familiar with. They're available in a variety of colors. And they're capable of converting electricity to light with high efficiency. Now let's start thinking about how a diode functions. What enables the light-emitting diode to emit light? Why do diodes block reverse current? To do this, we'll need a better understanding of semiconductors. Semiconductors are made of elements in this column of the periodic table starting with carbon. Carbon, silicon, and germanium all function as semiconductors. Tin less so. Once you get low in the periodic table, everything wants to act like a metal, with many exceptions. This is not intended to be a chemistry class. Anyway, carbon, silicon, and germanium all have 4 valence electrons. That is, they have 4 electrons that they can share with other atoms. So, let's start, if I can get my very amazing document camera working, by drawing a 2D view of one crystal of, let's say, silicon. Let's draw some happy little silicon atoms in their crystalline form, and they've each got 4 electrons around them, and because each one wants part ownership share of 8 total electrons, each atom is satisfied. Every atom wants 8 electrons in its outer shell, except for hydrogen and helium, that only want 2. Now, this crystal of pure silicon, let's say, is not going to be conductive. That is because all of the electrons are tied up in these covalent bonds here. There are no free charge carriers to function as conductors to allow a current to flow. So, intrinsic semiconductor is a crystal of pure silicon, carbon, or germanium. At room temperature, it is a poor conductor, but if you heat it up, then it will be capable of conducting a higher current. And this is because heat will jostle these electrons free from their bonds, and so you'll end up with loose electrons and gaps where the electrons would be. Now, the loose electrons, of course, flow from minus to plus, and the gaps will flow from plus to minus. That said, completely pure semiconductors are not usually used for any practical purpose. However, you can make them conductive, and this is done by introducing small quantities of other atoms called dopants. Now, if you note the periodic table here, we're looking at the column contains carbon, silicon, germanium. These atoms all have 4 electrons in their outer shell. Now, nitrogen, phosphorus, and arsenic all have 5, while boron, aluminum, and gallium all have 3. So, let's suppose we add an atom of boron to our crystal of carbon, silicon, or germanium. And then let's make a different crystal. I think we'll add phosphorus to that one. And then we draw our happy little silicon atoms. Happy, happy little silicon atoms. I'd love to tell you that there are no mistakes, only happy little accidents, but in electronics, happy accidents are rare. It's something like an evil Lego set, where if you place one piece wrong, it catches on fire and you have to start over. But these silicon atoms all have 4 electrons in their outer shell. However, this boron here only has 3. So it leaves a gap that is positively charged, called a hole, shockingly enough. And this phosphorus here, well, it has an extra electron that's just hanging out. So the upshot of this is that now these respective pieces of crystal behave differently. They both have free charge carriers. The one that has boron is called p-type silicon. It has holes in the number of electrons that should be in the crystal matrix, and these holes can move around, which means that it has a current carrying medium. Likewise, the n-type semiconductor has extra electrons, which can also be moved around. So, while intrinsic semiconductor is a poor conductor unless you heat it enough to jostle these electrons free, p-type semiconductor and n-type semiconductor will both conduct reasonably well at room temperature. By themselves, this isn't very exciting. Copper and silver, for example, are much better conductors than these are. That's why they're called semiconductors. But putting them together, that is where the real magic begins to happen. A note about which of the things in this column we've been using, this column of the periodic table that is. Originally, most semiconductor transistors were made from germanium. Nowadays, they're made from silicon. Some are made from silicon carbide. And the plan for the future, as I understand it, is to switch to pure carbon, which means we will have little chunks of diamond with dopant in them, functioning as our future semiconductor circuits. But back to the matter at hand, we have p-type semiconductor. Next to n-type semiconductor, we're going to zoom out a bit. No longer looking at individual atoms. So what happens here at the junction where these two things meet is that because all the atoms are still jostling around, even at room temperature, everything is wiggling at a subatomic level, these electrons and holes can diffuse around. You've got your little very badly drawn holes on the left side, little extra electrons on the right, and at this junction here, electrons that diffuse over it will fall into the holes, filling in the gaps in the electron bonds in the crystal matrix. So what you end up with is an area where there are no free charge carriers. This is called the depletion region or the depletion zone. It forms a non-conductive layer exactly at the p-n junction. Now the really interesting thing is what happens if you apply an external voltage. Suppose we put a cell from a battery in connection with this. Now, conventional current will tend to flow this way, but for this we're going to look electrostatically. So there will be a positive charge induced here because it's connected to the positive terminal. The other end is connected to the negative terminal here. Because like charges repel, the free electrons in the semiconductor matrix will be pushed this direction. Likewise, the free holes will be pushed this direction. The effect this has is to make the depletion region smaller. Apply more voltage, it shrinks further, until it stops existing entirely. Current will now flow through the device. One way to think of it is that extra holes are added on this side, extra electrons are added on this side, and then at the middle, the electron falls into the hole. Now, an electron falling into a hole means that it loses several energy levels. In order to maintain conservation of energy, this results in the release of a photon. This is where the light in light-emitting diodes comes from. Now consider what happens if you reverse the applied voltage. Starting with the same p-n junction, when the applied voltage is reversed, opposite charges attract. What this means is that now there is a positive charge here. This draws the electrons away from the junction. The negative charge here, likewise, attracts the holes. This causes the depletion zone to widen. The net effect is that applying voltage one way crunches the depletion zone down to a thickness of 0 and allows a current to flow, while the other way, it expands it. It increases the thickness of the non-conductive layer, so the device only conducts current in one direction. There are asterisks. You can force it. If you apply enough voltage to it in the reverse biased direction, say by stacking some more cells, you can get a very high voltage gradient going on here. Then what happens? Well, because we are at room temperature and the atoms are all jostling, sooner or later, by chance, a free hole might appear on this side as a result of the atoms moving around and one of the electrons being shaken loose from its orbit. But then because of the high potential gradient, it will be very strongly pushed that way, smacking into another atom and freeing another couple of holes, and so on and so forth, until you end up with a huge avalanche of charge carriers. This is called, unsurprisingly enough, avalanche breakdown. if you reverse bias your diodes enough, you can force them to conduct. If you apply enough voltage, you can get anything to conduct. Don't you worry. You can get very interesting things with high voltage. Mineral oil will crawl up your wires because it is attracted to that which is inside. And why were you immersing your wires in mineral oil? Because the air will break down if you leave them in open air because of corona discharge. Anyway, diode, PN junction. That is what makes a diode. Here is the schematic symbol for a diode. It's this beautiful little arrow thing with an extra line. It allows conventional current to flow this way. LEDs are the same symbol, but they have two little arrows to indicate the light is coming out of them. However, because all PN junction diodes work by collapsing a depletion zone and causing the electrons on one side to fall into the holes in the other, dropping several energy levels in the process, this means that all diodes emit light. It's just that regular silicon diodes don't emit visible light. Us puny humans cannot see it. Tragic. I know you're all very cut up about this. Now, on a more practical note, let's see if I can find the entire book of diodes that I've been keeping around here. Nope, just resistors. There we go. So I started off by showing you through hole 1N4004. It's a very common type of diode, but now that we are in the future, in the far-off year of 2025, diodes are more likely to be surface mount parts. That is, parts that do not have any external leads. So here are some diodes. These ones, as you can see, do not have external leads. Sometimes you might see them in glass cases, as they are here, as they would have been in the before time, the long, long ago, when a common diode might look something like this. However, more often than not, you'll simply see a relatively difficult to identify black box, a literal black box, with striping on one side to indicate where the cathode is, the minus terminal. See, these are Schottky diodes. We'll get into that later. These ones look like regular PN junction diodes. But so, try to end these things with something practical, rather than just me gesticulating at these beautiful diagrams. One other thing I should mention: when the depletion zone forms, it has a bit of an electric field associated with it that is internal to the depletion zone. Because this area used to have extra electrons, and they diffused over here, it has a slight positive charge. Because this area used to have extra holes, but they were filled in, it has a slight negative charge. Why does this matter, since it all stays internal to the diode? Well, for one, this is the region you have to squish flat if you want to promote conventional current flow through it. Which means that the diode, for a regular silicon diode, always burns off 0.7 volts. For a germanium diode, it's closer to 0.3, 0.4, but you will hardly ever see germanium diodes in real applications. So this is how much voltage a diode eats. 0.7 volts. That's how much it takes to turn it on. If you exceed that, its current will be functionally infinite. But back to this little space charge region. Let's imagine we were running an LED backwards. You want to send a photon in instead of having them come out. This photon smacks into an electron that's associated with an atom, splitting it into an electron and a hole, splitting the location that was occupied by the electron in the crystal structure. That is, it smacks an electron out of place. Where the electron was, a hole is left, and of course there's the original electron still wandering around somewhere. But because the electron is negatively charged, it gets pulled over here to the positive, and the hole is likewise pulled over here. So what this means is that if you add a photon and it smacks an electron out of place, the space charge region tends to pull the resultant hole in electron to opposite sides of the p-n junction, which means you can use one of these to convert light into electricity. This principle has found wide application nowadays. You can technically measure the voltage produced by shining light at an LED, but it is very difficult to do. However, they make special diodes that have a wide surface area that are intended specifically for this application. They're called solar cells. That is how they work. Now let's see. Trying to shoot for about a half hour, so I think I have time to do the practical experiment here. I will try. I'm going to be taking an assortment of diodes of different colors. Looks like I have red. Then, in this case, I'll have the remainder of them. Common colors. You can get LEDs in a wide variety of other colors, but I do not have them on hand. So I'm going to give each LED its own 1 kiloohm safety current limiting resistor. If you just want to build things with LEDs, if that's why you're here watching this, use a kiloohm. As long as the supply voltage isn't greater than 20 volts, it'll work for everything. For every standard 5mm LED, that is. Putting 1 kiloohm in series with it will prevent it from conducting so much current that it burns up. But I'm not sure why you're here. And I started this by saying that I would cover everything, which I am realizing is going to take a long time. So, well, you know, how do you eat an elephant? One piece at a time. So we have red, yellow, then green, then blue. You will note that this order is going in the same order as the colors of the rainbow. The reason why will be explained shortly. Explained by me. Now I need some 1 kiloohm resistors. Ooh, really? Shouldn't have spent so much time teaching you theory. Now I'm running out of time for the practical stuff. Dang. It's my intention to go back and forth over and over throughout this entire series. Theory, application, theory, application. Because those classes where you spend weeks doing nothing but learning theories with no application, they are not a fun time. I think we can all agree on that. So, this circuit is going to have the LED connected to this positive rail, and then it'll get a resistor going back to the negative rail, like so. So, I see I've already started with the wrong color. Well, why would it be any different? All right. So, red. Red is the first color in the rainbow. Well, it's sort of infrared, but I'll have to show you guys a picture of the whole electromagnetic spectrum. We humans only get a little piece of it. It's kind of sad. Though I guess nowadays there should be the technology to extend it beyond, extend your vision beyond the normal electromagnetic spectrum. See ultraviolet like bees do. Red, yellow, green. Action-packed. I guess I could be more exciting. I don't know if it's worth it though. Well, and also if I try to get too exciting and flashy, then I'm not really going to help much with internalizing learning. All that learning, you know, very important. All right, so we're going to power these up. Then what I'm going to do is measure the forward voltage drop of each of these. That is, how much voltage it takes to turn them on. Roughly. We'll get into VI curves later. I've already, well, it is no matter. It's always something. So, there are the negatives. Here are the positives. This will be 2 parts.